everyone, good afternoon and welcome to this webinar. Today's webinar is about model coupling with OpenMI, and in the next 90 minutes we will introduce you to OpenMI, we will explain the most important concepts of model coupling, and we will give you a live demonstration how to use OpenMI. This webinar is given in the frame of the EU research project CyberNet, which is the Critical Infrastructures, Preparedness and Resilience Research Network. First, allow me to introduce ourselves. With me today is Bernhard Becker, OpenMI expert at Deltares. My name is Andreas Bussel. I'm a flood risk analyst at Deltares, and we are both situated in Delft, the Netherlands. The goal of this webinar is to demonstrate the coupling of water-related models using OpenMI 1.4, SOBEK 3 and RTC tools. And we would like to inform you that everyone can ask questions during this webinar. We will have 3 interactive Q&A sessions. You can provide your questions using the chat, but you can also raise your hands and speak with us if you have a microphone. Also, we would like to emphasize that a recorded version of this webinar will be available from the Deltares Academy website in a couple of days. Let's have a quick look on the schedule of today. We will start with an introduction on what is OpenMI. Bernhard will give some example application cases. I will give an introduction on the case study for the live demonstration. Bernhard will show you how to use OpenMI to couple water-related models with SOBEK and RTC tools. And afterwards, we will have a deeper look into the software and how to migrate your own code to OpenMI compliance. At the end, we will give you some take-home messages before we wrap up the webinar. Okay, let's get started with the first question. What is OpenMI? OpenMI is an open model interface standard for hydro-related models, and it's developed by the OpenMI Association. It is designed for water-related models, for existing and for new code. And OpenMI allows to do data exchange during runtime per time step. OpenMI is an open source OGC standard. The OpenMI 2.0 is published under OGC standard. And currently there are more than 30 models already OpenMI compliant. You can check the website of OpenMI at www.openmi.org to see a list of these models. Last year, OpenMI celebrated its 10th birthday, and all started in 2005 with the HarmonIT project. OpenMI was developed by 14 different organizations from 7 countries in the EU project HarmonIT in order to facilitate the simulation of interacting processes, particularly environmental processes. And the first version has been released at the OpenMI standard 1.0 in a .NET framework. There was a follow-up project, the OpenMI Live, which resulted in further developments in a smaller consortium of 10 partners from 5 different countries, and the release of the OpenMI 1.4. It's available as .NET and Java, and also the foundation of the OpenMI Association. In 2013, OpenMI 2.0 has been released. It's an OGC standard, and it has several new features. For example, a more flexible way of linking, more flexibility in the overall control flow, and less differences between temporal and spatial models. There is a new user interface and also a software development kit available. Now, today we have the OpenMI webinar, and we would like to present OpenMI to a broader audience of experts and students in this webinar. So who should apply OpenMI? Looking at the website from OpenMI Live, they state the long-term aim is that OpenMI should become the European and global standard for modeling in the environmental domain. So it could be researchers that develop source code for their studies, and they can couple it with OpenMI compliant models. It could be developers of integrated hydrological modeling tools, for example the coupling of surface and subsurface flood models. or consultants that need dedicated model coupling using a flexible but standardized coupling technique and use the OpenMI standard for more than one coupling task. It could be also multidisciplinary studies like the CyberNet project, where it's about the coupling of different CI models. After this short introduction, I would like to give the word to Bernhard, who will answer the question, what is a model? Bernhard, the floor is yours.
Yeah, hello everybody. Thank you, Andreas. What is a model? I mean, what is a model for this webinar? So we use the term model as a conceptual model when we ask the question, how does a system operate in a very generic way? So for example, water follows gravity and we have mass conservation. These are conceptual models. If we put this into equations or a set of equations, then we get a mathematical model, and that can be deterministic or physics-based, but also empirical, statistical, or logical. And these equations coded into computer code gives us a computer model. And generic model is a term we use also for simulation software, and usually, but not necessarily, simulation software has a graphical user interface and some standards for input and output files. And if we have a generic model and add some site-specific data, then we get a site-specific model. So this is how we will use the word model for this webinar. And next topic is when to apply OpenMI. And we have two categories. The first one is coupling of different processes. So this means we have different models for different processes, one model for each process. And both processes are of similar relevance. But these processes can also be on different time scales. There's also another category of applications, and this is coupling of models of the same type. And if there are different models that belong to different institutions but somehow relate to each other, maybe have shared boundaries, then it makes sense, or it can be necessary to couple them. And usually these models, as they are owned by different people, they are used coupled and uncoupled, and they will always have a different state of maintenance, will be calibrated individually, and will be used uncoupled for local studies. And we start with such an example here. This is the first example case where we have the coupling of two channel flow models. Here on this map you see the channel flow models for the water authority Friesland, the blue model, and water authority Noord-Zuidwest, the red model here. This is the northern part of the Netherlands, and these two models are coupled at 3 connection points here, and that's the second one and the third one, so they have shared boundaries. But in fact this is one water system but 2 water authorities, and the water does not care about this administrative boundary here in between. And so it makes sense to couple these two models in order to represent the water system as a whole. And we can see some results here in these two graphs. We have water discharge over time here and water level over time here. And the red graphs, the red curves are related to this Noord-Zuidwest model, and then blue are related to the Friesland model. And what you what we can see here, let's start with the water levels. If we couple these models, so these are the blue and the red lines, then we get the same water level, and this is not the case if we have uncoupled models. So then we have water level in the blue model here, and this is the one from the corresponding one from the red model. And this line indicates the difference in the uncoupled versions. And this dark green line here says that we have no difference in water levels. So this is one benefit. And for the discharge, we have a slightly different view. There's only small differences in both cases. But what we also can see that the coupled result here, these are the lines for the coupled result, they are different than in the uncoupled case. So this is one benefit of model coupling. We get a more accurate view of the whole system at the shared boundaries. Then we have another case. It's again coupling of models of the same type. We have a large-scale SOBEK model for the Netherlands. Here, this is again the north of the Netherlands. And we used to look at this blue model here, Noorder-Zeivest and Friesland from the previous slide. But there are more, but they are all on a coarser grid. And the idea is that we can connect these submodels to one big SOBEK model for the whole of the Netherlands and replace on demand these submodels with more detailed models, like we have seen in the previous slide. And here we have set up an OpenMI composition with 6 SOBEK models. Each yellow box is representing one model, and they are connected with each other. Then another example case for coupling of models of different types. So there are 2 models representing different processes, one model for surface water flow and one model for groundwater flow. What we see here is a cross-sectional view of an aquifer, and here's a river, and we will see in this movie that the water level rises, and the question is, how does the groundwater react on this rising water level? And we have some inundations here as well. In fact, you see 2 model results. The blue one assumes saturated flow only, and the red result represents simulation results from variably saturated flow. So this example has been designed for comparison. You see some differences here, but in principle the water level, the groundwater level follows here the surface water level, but now here the flood wave has already passed and the water level is declined already, but here we have still some increasing water level, so there's a subsurface flood wave moving towards that direction and following the river flood wave with delay. So this OpenMI composition consists of an Elbe flood model and a FIFLO groundwater model, and the Elbe flood model produces water level, and these are fed to a leakage boundary condition in FIFLO, and the corresponding flow is passed back to the Elbe flood model. The next example, again 2 different processes, channel flow and industrial hydraulics. Here the question was to design or to derive design parameters for a pump station for Lake Lauwersmeer, again in the Netherlands, northern part. Here we see the Lake Lauwersmeer represented with a SOBEK flow model with 2 hydraulic structures, the pump station and the slice. And this model is coupled via OpenMI to a Wanda model, and this model, Wanda, is able to represent the pump and sluice hydraulics in more detail than SOBEK is able. And the problem here is that we expect more extreme rainfall events and rising sea levels here. This is the Wadden Sea, North Sea. And the problem is that this land is located below sea level. And in the future we expect that the drainage of this land must be facilitated with a pump station. And here in this figure, on this slide, some simulation results. Discharge over time, computed from the Wanda model and is used as input in the SOBEK open channel flow model. So this is kind of boundary condition. And then we have here the pressure head over time, and this is computed by SOBEK. And what you can see here, this is the water level on the sea side. For each color represents one pumping unit. And here you see the water level on the inland, and the inland water system water level is lower than the sea water level. And then the power consumption, again computed by Wanda. This is interesting for designing the pump station. This is power consumption over time, also for different pumping units that are active during this scenario. Another example, channel flow coupled with human operations. This is the case of the Upper Rhine water system in Germany. Here we have a close-up of the SOBEK model. This is the main channel of the River Rhine, and then we have a retention basin here and a hydraulic structure to open this or to activate this retention basin during high water to store water in this area. And the hydraulics are represented with the SOBEK open channel flow model. And then we have RTC tools, which is a generic model for real-time control for the human operations. And in fact, there are some decision trees behind, and SOBEK produces channel flow parameters, discharges and water levels, and RTC tools uses this water system state in order to derive the control parameter according to the operational protocols that are modeled with decision trees. And then RTC tools produces crest levels and turbine discharges, and these are passed back to SOBEK and used in the channel flow model.
Thank you, Bernhard, for this broad overview of possibilities to use OpenMI. It's now time for the first Q&A block, and I'm sure we already received some questions. The first question, Bernhard, I've received is, can you give an overview about software models which I can couple using OpenMI?
Okay, well, I will not present an overview of OpenMI compliant models now, but you can get this overview via the OpenMI website, and I think the link is in one of our previous slides. So please consult the OpenMI website for a list of OpenMI compliant models.
Okay, thank you. Yeah, it's openmi.org, and then under the link OpenMI around the world, I guess it's a list of software available under OpenMI compliance. We would have a question to the audience, actually. Maybe you can provide via the chat what you would like to intend to couple, and we can take this into consideration during the later Q&A blocks. If there are no further questions, Bernhard, I see one more question. One question, is OpenMI compliant models free or commercial, Bernhard?
Yeah, well, there's no yes or no. This depends on the software provider. Usually, if you have a license for, if you have a commercial model where you need a license, then the OpenMI compliant version will be also usually under this license. But there are also open source models that are used for free, independent if you use them within an OpenMI composition or not. One example is the RTC tools that we are using during this webinar. This is an open source package, and you can have that for free.
Thanks, Bernhard. I see another question, which is, I have seen that SWOT has been made OpenMI compliant. What about we use the latest version of SWOT? Do you know SWOT, Bernhard?
I'm not familiar with SWOT, but the general procedure is that you contact the software provider with respect to any questions on the OpenMI interface, because they have made this interface and it will know what's in it and under which terms they can be used and with which OpenMI version.
Okay, yeah, thank you very much, Bernhard. I think it's time to have a look on the different aspects of model coupling now. Bernhard, it's yours.
Yeah, some more background on model coupling or conjunctive modeling. There are different terms for model coupling or conjunctive modeling or linked modeling or integrated modeling, and what we will use within this webinar is that conjunctive modeling is a more general term. This means that we link models to model process interaction in some way, and then we can choose between coupled modeling and uncoupled conjunctive modeling. Coupled modeling means that we have data transfer in two directions, and this requires data exchange on a time-step basis. And contrary, uncoupled conjunctive modeling would mean that we have data transfer in only one direction, and this not necessarily means that we need to exchange data on a time-step basis. It can make sense, but you can also run the whole simulation period of one model, feed that data to the next model after some processing, so that you not necessarily need to exchange data per time step. Here's some figures to illustrate this a bit more in detail. So this is the uncoupled model approach. We have 4 models, and here the solid arrow means data exchange or data transfer from model C to model B, for example, and this is the corresponding data need or data request. So you could first run this model for the whole simulation period and then transfer the data to the component C and so on. If we have a coupled situation, like here in this right figure, component B and component C, then we have data transfer in two directions. So model B requests data from model C, but in order to answer that request, model C needs also data from model B. So this means that what component B produces has an effect on the result of model C and vice versa, so that means that we have to exchange data on a time-step basis. And of course this bidirectional link can be again connected in a unidirectional way to another component. So for model coupling, data exchange in both directions, we have 3 different categories again, and this is external coupling, iterative coupling, and the simultaneous solution. Let's start with the external coupling, which is the easiest to implement, but also the least accurate one, because we always, in most cases we'll have mass balance errors. Let's say we have a model A with the timeline here and some discrete time steps 1, 2, 3, and model B with the same timeline. Then model A results would be used by model B as boundary conditions, BC boundary condition, and R as result. And then model B could proceed to the second time step. It will produce results itself, and these are used then as boundary conditions for model A, and model A can compute the second time step, and so on. So there's a time lag here. Model A gets fresh data from B, but B gets outdated data from model A. And to overcome this problem, it's possible to apply iterative coupling, and this would mean that we use the results as a first guess for model B in this case. Then the results are provided to model A, and model A computes results, and these again are used as boundary condition for model B for time step 2, and we continue this iteration loop until an accuracy criterion is fulfilled. So this means a bit more advanced coupling. It is more accurate, needs a bit more coding of course, but it will be also computationally more expensive because we will you have to iterate the time steps or to repeat the time steps. And then, just for completeness, the simultaneous solution, if we have two or more processes, then we would put them into one equation system and solve them simultaneously. This is the highest level of model coupling. It is accurate, but the time step resolution must be the same, and equations should be of the same type. Otherwise, the solver will not enjoy that very much. In this webinar, we will only deal with these two, or in fact with that one. OpenMI supports only these two coupling methods.
Thank you, Bernhard, for the overview on model coupling. I see that there are a couple of questions on this topic already. First question, when do I have to apply iterative coupling, and when is external coupling sufficient? Bernhard, can you say something on this?
Yeah, this depends on the case, of course. The general recommendation is that you start with external coupling and analyze the results. And in many cases, if the time steps are small enough, then this will do it. We've also published a technical exercise on this topic that can you give some guidance, and the reference can be seen in the accompanying course material that we will provide with this webinar. But if you find that this is not sufficient, then it might make sense to apply iterative coupling.
Okay, thanks. Another question, why does OpenMI not support simultaneous coupling?
Yeah, simultaneous model coupling. Yeah, this means that we put everything into one equation system, and there's no way to make this generic. So it is not possible to offer this in a generic way with OpenMI, because we have to go deeper into the code, into the setup of the equation system. And what we do with external and iterative coupling is, more or less data exchange, but not data exchange after solving the equation system.
So you keep the model separate, the software separate, but you get them talking.
Yes, yeah, so it's more talking between models and not integrating the equation systems. Yeah, that's it.
Okay. Can you say something about the computation times, Bernhard?
Computing times usually in OpenMI 1.4, they add up because we have a request and reply mechanism. So one model is computing, produces data, and then this data is taken by the second model, and the first model waits. So it adds up. And if you have iterative coupling, then it adds up again, but it depends on the number of iterations that are necessary.
Okay, thank you.
Okay, let's continue. I think this is for you, Andreas.
Yeah. I would like to introduce the live demonstration. This case study is actually situated at the Elbe River around Magdeburg in Germany, but I would like to highlight that the scenario and also the data we will use, they are imaginary. In this case study, we want to have a look on a flood event which happened in 2013 and which had a major impact on different critical infrastructures. Actually, at the end of May 2013, there was a low pressure system over entire Central Europe, and already there were highly saturated soils in Austria and in Germany, but 400 millimeters of rainfall within 4 days, which led to the highest water levels which have been observed so far along the Elbe, along the Danube, and also their tributaries. And during this major flood event, there were several impacts on critical infrastructure. For example, there were damages on a high-speed railway in Germany at the Elbe River, which was out of service for more than 5 months. There was also flooding of major highways along the Danube River with a breakdown of more than 4 weeks. And there was the potential flooding of a power distribution station close to Magdeburg with an expected breakdown of significantly more than 12 months. Let's have a look into the situation at the Elbe River basin. What you can see on the left-hand side is the amount of rainfall within 72 hours. You can see that there were up to 100 liters per square meter of rainfall. And remember, the soils in this area were already highly saturated, so they had no capacity to keep the rainfall. And on the right-hand side, you can see the affected areas in Central Europe along the Danube River, but also in the Elbe River basin. Magdeburg is located in the small circle at the downstream of the Elbe River. And if we zoom in this area, we can see the extent of the flooding on the left-hand side. It's a major flooding of the entire river and the area around it. And there were major efforts to strengthen and secure the dikes in this area, among others to keep this power distribution station nearby Magdeburg dry. In this scenario, it's about the power distribution station Rotensee, which is a 110,000 volt local power distribution station. It's responsible for about 30,000 households, industry in the area, but also major infrastructures. And it was, during these days, urgently required to pump floodwater, drinking water, but other vital services. And it was not known what would happen in terms of cascading effects if this transformator station would have been flooded. The power distribution station is really close to the Elbe River. It's significantly lower than the floodwater level, and it was temporarily secured by a sandbag barrier. The question now for this demonstration is how we would model such a case and how we can benefit from model coupling. And that's for Bernhard.
Thank you. So the modeling question that we have is, sorry, this is the situation in a modeling point of view. So we have our river system here, and we have a weir here. This is the gauge Magdeburg as downstream boundary condition. So the water is flowing from south to north. And here we have the upstream boundary condition. Then we have a bifurcation here, and with the main river channel here, and this is close to the city center, and we have the old Elbe branch here, and the critical infrastructure here, railway track junctions, the main railway station, and the power substation. Question is, how can we control the weir in such a way that the water level in the main river remains below the flood warning level, which is 54.75 meters? And our approach is, so we have here the river system, and this is a hydraulic structure. The approach is that we couple the model for open channel flow and real-time control. And I would like to introduce those two models first to you. So again, here this overview to introduce the open channel flow model. And I already have mentioned the hydraulic objects here, the hydraulic structure, the weir, and the downstream and upstream boundary condition. But also of interest are these two observation points that we have introduced here. So here we look at in terms of the warning level, and this is the control point, and we say if something happens here, then we close this weir. I have to leave the presentation now and go into the SOBEK user interface in order to show what's happening without control. So we have here the SOBEK graphical user interface. Again here the river network with the two parallel channels and the observation points, and here this weir. I will first switch off the nodes that you can see where this weir is and zoom in a little bit to give you a better impression of this bifurcation area. So here the water can flow along the main river channel, and we also we can control the flow through this old Elbe river here with the help of this weir. What's happening here? I will first show you a side view animation about this part of the river section. So here we see the weir, and this is the upstream observation point. And I will add the crest level, which is represented by this orange ball here. And now you see the water level rising, and the weir is closed all the time, and you see that there's some backwater effect, but there's in fact no water flowing through this old Elbe river branch. Okay, now we have declining high water, and I go back to show you the next side view. And instead of the old Elbe river branch, I choose the main channel. So that's this coverage here. Again, the side view. And now we have another observation point. This is the one with the warning level. And now the channel is filled with water. The warning level is 54.75, so somewhere here. And now we see that the high water flood wave comes, and we see also that the warning level is exceeded. So this gives you an impression about what's happening in this river system, and we want now to add the process of controlling or operating the weir in such a way that we do not exceed the flood warning level here at this observation point. I go back to the presentation, and I briefly introduced there it is, the real-time control model. This is a very simple model. The generic code is RTC tools. RTC is real-time control, and RTC tools is a toolbox for modeling real-time control. So this is not a physics-based model, but a logical or relational model. And the only thing we use here is the decision tree. So we have the observation point upstream, and we evaluate the water level here. Is the water level larger than 57 meters? Yes, then we open the weir, and if not, the weir is closed. In both cases, the crest level is an output of this model, and we use this and feed it to SOBEK for the hydraulic model. Okay, so when we summarize, then we have two processes, the open channel flow and the human operations. And human operations, this means the control of hydraulic structures in this case, or the control of the hydraulic structure. And for open channel flow, we have the SOBEK simulation program, or site-specific model. And for control RTC tools, SOBEK produces water levels and discharges, but we use the water level for RTC tools. With the help of this water level, RTC tools can give us a crest level, and this crest level will be used as input parameter for SOBEK and has an effect on water levels and discharges. This is how the OpenMI composition should look like. So we have one yellow box for each model component, and I will show you now how to put this all together. I go to my file system here. I start the OpenMI configuration editor. I prepared a batch file for that. So now this is an empty OpenMI composition. The first step is to add the model, and I've prepared an RTC tools OpenMI configuration file for that. There it is. And now the next model, add model, and this is the Elbe SOBEK model. This takes some more seconds to load it because this is a more complex model. There it is. So now I have the integrated model. Well, all SOBEK models get the name integrated model because there's the potential to have an integrated model with that. Now the coupling, I choose Add Connection from the Composition menu, and then the mouse pointer says what to do. Select Source. So first data from SOBEK to RTC tools, and a mouse click on this connection opens the connection properties window. And here I see output exchange items from the integrated model, which is SOBEK, and here the input exchange items for RTC tools. And SOBEK has a very wide range of options here, and what I need is the water level at the observation point number 1. So there are 2 observation points, and I now choose the corresponding item in RTC tools. And here the modeler has chosen to use similar names for similar objects. So the observation point number 1 appears in both models. Yeah, of course it represents somehow the same location or the same spot, so this makes sense. So now I have my connection ready. I apply this, and then we see here what's happening. Water level from observation point 1 is used as water level for observation point 1. Close. And now the feedback, composition, add connection. Source is now the RTC tools model, and target is the integrated model, the SOBEK model. Again, the connection properties. And now RTC tools offers me exactly 1 crest level here. And for SOBEK, the list of input exchange items is also smaller than in the previous window, and I use the crest level for where number 1, again as crest level where number 1, apply, close. Okay, so now the connection is ready, and now we need some more items, a trigger element, and this trigger element triggers or starts the simulation, and I will explain that later in more detail. And we need also a connection from the integrated model to the trigger. And here we again have the connection properties, and it does not really matter what we connect, it's simply important to have some connection, and I connect the observation point number 2 with the trigger element, apply. Okay, so now our OpenMI composition is ready, and the next thing is to go to the Run Properties menu. Here are some events listened options. I set them all, and then we have the invoke trigger add item here. Makes sense to check the overlapping of simulation periods. In our case they are all the same, so this is all fine. And then I hit the run button. Let's see what's happening. We see the simulation progress here in this progress window, and here on the right column the simulation time and a lot of events that are recorded during the simulation progress. And the sender, we have sometimes RTC tools and also integrated model, and data changed and targets after and source before and so on. So this is all recorded also in a log file that you can specify in the Run Properties window. And now we proceed until 25th January 2000, and there we come to an end. And here we see the important message for the global progress that the simulation finished successfully. I will close this window, and now we see that all boxes are grayed out. This means that something has changed in the composition. I do now the exit, push the exit button, and I choose not to save this composition. So that was the demonstration of the setting up the composition and doing a simulation run. But now we want to see what the effect on the simulation results is. So I switch again Windows, back to the SOBEK user interface, and I will have to load another model. I configured the SOBEK model in such a way that the results are written to a new SOBEK project. I call that Magdeburg RTC, and I load that. Let's see what's happening. So this is the same model but with different results, and they should be influenced by the coupling with RTC tools. Let me see. Here, zoom to extent of the network. So this is familiar, I think. And let's first again look at this route with the old Elbe river branch, side view, and I will add this coverage crest level. Now the water comes. Please look here at the water level, 57. There it is. The crest level is going down when we hit the 57 mark here. And we see also a clear effect here that water is flowing through this channel, no longer only these backwater effects. And now the crest level, yeah, we have passed this 57 mark. The crest level is up again. Once again maybe, so look here, so the observation point is here, so I must point my mouse here. Okay, there it is. Okay, once again, so now the flood wave, the water level goes down and the crest level goes up. Okay, let's move to the next route here with the main channel. Then we do not see the where, but the second observation point with the warning level, a bit below 55. And let's see what's happening. So I put my mouse here, 55. There you see the effect of opening the second river section, and we are now far below this warning level. And now the flood wave has passed. So now the way is closed. So this looks good. Okay. Back to the presentation, back to the slides. To illustrate the effect or the benefit of model coupling a bit more, I prepared these two graphs here. And on the left side we see the results from SOBEK uncoupled, and on the right hand side we have SOBEK coupled with RTC tools. This green line represents the crest level of the weir. Here it remains closed all the time, and here we have it open at a point in time where this blue line here, dark blue line, which is the water level at observation point 1, hits the 57 water level, and this is what we have seen in our flow chart for the RTC tools model. If the water level is larger than 57, we open the weir, and if it's smaller than 57, we close the weir. This red line here is the flood warning level, and the light blue line is the water level at observation point 2. And now we are below the flood warning level, and in this simulation the water level was above the flood warning level. You can see here at that point in time when the weir opens, this effect that water is released through this second branch and reduces the water level. So this can be seen here also very well. Okay, that is what I want to show.
Thank you, Bernhard, for the demonstration and for showing us how we can use coupling of two different models. It shows how it impacts the results and how we can benefit to answer this modeling question. Of course, it was a very simplified example, but I hope for the audience we were able to show it. I see that there are a couple of questions. The first question is, I understand that SOBEK has a model for real-time control with RTC tools included. So what is the added value for coupling with OpenMI?
Yeah, indeed, SOBEK does have an RTC module included. So that's what I meant with potential for integrated modeling. We call this DRTC, and it uses RTC tools as a computational core. So what we have presented here can also be done within SOBEK without OpenMI. But not all features that RTC tools supports are accessible via SOBEK, via the DRTC module. So with OpenMI, we can address more features from RTC tools. That's the first one. And the second issue that I would like to mention is this OpenMI coupling was earlier, so you can use OpenMI also for piloting. So if you couple two models with OpenMI, you can show that it works and what the added value is. And then the next step could be to not only integrate data exchange, but also integrate user interfaces.
Okay. So if I can summarize it, the simple questions can be answered in SOBEK directly, but as soon as it's more complicated, then you would suggest to use the two software independently and use OpenMI to couple them.
Yeah.
Okay. There is another question. What is the process for creating OpenMI versions of models, the OMI files, to insert them into the OpenMI initial menu?
I will go into details later, so I suggest that we bring up this question in the next questions and answer block.
Okay.
Because I think that's a part of this question will be answered, and if not, then we can at least clarify a bit more.
Okay.
Would that be okay?
Perfect, yeah.
So we can come back to that later.
And another question then, was the model coupled with other models for modeling, for example, the impacts of critical infrastructure? Can we do this in OpenMI?
You mean within the CyberNet project?
Yep.
Well, we have not applied OpenMI to couple the critical infrastructure models. What we had in that case was that we have flood scenarios, but this was an unidirectional link, so the critical infrastructure in that case had no impact on the flooding, so we did not have to couple the flooding process with other models. So the answer is no.
Okay.
But could have been done with OpenMI as well.
Could have been done.
Yeah.
Okay. Well then, thanks a lot for providing those interesting questions. Understood that we now have a deeper look into the OpenMI standard and into the coding. And I made a mistake in the beginning. We will have 4 Q&A blocks, not only 3, so there will be one more Q&A afterwards to answer your questions. Bernhard.
Okay. Yeah, what I promised was to say a bit more about what the trigger, what the role of the trigger is, and I will do that now. So you remember this OpenMi-Composition, and I added this blue element, the trigger. And I also have already mentioned that we have a request-reply mechanism that coordinates the data exchange within OpenMI. And we made this picture, this figure, to illustrate that. So the role of the trigger is to start the whole coupled simulation, and the trigger asks the first question, and this, yeah, we can say, give me some results at the end of the simulation period here after time step 100. And this question is asked to SOBEK, and SOBEK says, yes, I can do that. So I have to proceed from my initial condition from T0 to T100, but I need some data first. I need something from RTC tools, and this is the crest level. So there's another question sent to RTC tools. So we are now here in this. So this is a chain of questions, and RTC tools says, yes, I could give you the crest level, but I need something from you first, and this is the water level. And SOBEK says, okay, then you get the water level that I have, water level at time step 0, and with that water level, RTC tools can do his computation. After that, it has proceeded to time step 1 and is now able to answer this question here in step 2, this one. And with that information, SOBEK is also able to compute, to proceed from time step 0 to time step 1. And then the whole thing continues in that pattern until SOBEK can answer this question. So this is the role of the trigger and how the data exchange mechanism works. And there was one question, what about computing time? And I think this explains also why simulation times add up. In OpenMI 2.0, there are, in addition to this request and reply mechanism, also some other mechanisms where models can compute parallel. So this will speed up coupled simulations, but not in OpenMI 1.4. Sorry, this is what we are using here. Setting up an OpenMI composition. The modeler has to prepare at least one OMI file, and I think this is related to the question we just had within the Q&A block. This is an XML file, and this file must contain the following information. Where is the dynamic link library with the computational core and the OpenMI interface? Where are the input files? And maybe there's something else like command line arguments, or something like an output folder where to write the simulation results. And this is the case in the SOBEK model that I just presented. So what we do is loading OMI files that are prepared by the modeler, and then we can save the whole composition, and this will result in an OPR file, OpenMI project. And this is more about the relation between the components. Which components are involved? In our case, it's these two and the trigger. How are they coupled? This means, it's basically the information you fill in the connection properties. So data from here to there, and the exchange items that are connected. Also the information about the simulation period, and of course where the trigger is linked to. The way I connect, it makes a difference if I connect the trigger to a different model, because then we have a different model answering the first question, and we have a change in the order of computations. Some words on OpenMI Exchange items. You have seen in the connection properties that I connected output exchange items with input exchange items. Input exchange items usually are somehow boundary conditions or control states in our case. And in most cases, output exchange items will be simulation results or contain simulation results. And any exchange item always gives information about what it includes, so water level in meters, for example, discharges in cubic meter per second, or crest level in meters. And there's also the opportunity to convert units. And this next thing is where it applies, and we had, for example, the where number 1 and gauge Schönebeck or observation point 2 or something. In our case, we used simple names of model objects, but this can also be spatial related XY coordinates, for example, or 3-dimensional coordinates. That's also possible. OpenMI supports that. Next slide is about making my own code OpenMI compliant. And this is, I think, also related to the question that has been asked in the previous question and answer session. We need a dynamic link library with OpenMI functions. And this is basically what the OpenMI standard is about. We have OpenMI standard functions that must be somehow supported. And in this list I listed the most important ones. The first one is the initialize function. Within this function, usually the model input files are read, and all the exchange items that you can see in the connection properties, they are populated. For example, all water levels in meters at all node numbers, or only node number 62 if the programmer or developer chooses so. Second important OpenMI member function is the getCurrentTime, and this returns the current simulation time as modified Julian day. This is a standard to define points in time. So it's not about seconds, it's not about hours, it's not about days. It must be modified Julian day, even if your code maybe only takes minutes as time steps. So there must be somehow a reference day as well. Then we have get values and set values. Get values returns a simulation result for an output exchange item. Yeah, I said here simulation result, but it can also be a model parameter or a part of the schematization, for example, the XY coordinates of a specific node in the model grid. Set values is the contrary, the corresponding one. This sets a value for an input exchange item, in most cases boundary conditions. And then the most tricky one, perform time steps. We need a function that solves the model equations for one time step only. You have seen how the request and reply mechanism works, and OpenMI lets all the components proceed one time step and checks, do you need data, yes or no, and if so, it will provide the model with data. So it is on a time step base, so that's why we need to perform one time step. And this can make it very tricky. So here's some things to consider if you migrate your own legacy code. Maybe it's Fortran or C++ or Python. If you migrate that to OpenMI compliance, there are some guidelines from the OpenMI Association to help you with that, and also some examples. So the first thing is to reorganize the computational core. If you have an executable, then you organize it in such a way that you have an executable that invokes a DLL, and this DLL can be equipped with the OpenMI interface. Then we need to break up the big loop over all time steps, if you have that. Usually you have one big loop, but as I explained before, we need a function that performs only one time step. And later, next step is to provide internal functions to be able to fill all these OpenMI standard member functions. Examples how you could name these functions as compute one time step, return a list of nodes, return simulation time in seconds, and then you do something with that in order to get something in modified Julian day. Next step is to couple the computational core, we call it the engine in OpenMI, with the OpenMI source code. This is C# or Java, and in case of C#, you would use MSDN platform invoke. There are also some examples how you can do that. And then it's the final step is to fill in the OpenMI linkable engine, which is an interface with fill all the member functions with the help of the functions you have predefined here. Yeah, that was what I wanted to tell you about OpenMI behind the scenes. Now it's your turn, Andreas.
Yeah, thank you, Bernhard. Very interesting about the coding. We now have time for the last Q&A block. If you have questions, especially on this last subject, you're invited to raise them now. I see one question, Bernhard. User has a Sonvenant flow code. How long does it take to make the code OpenMI compliant?
Oh, yeah, this depends on the experience in programming. Do you have experience already with C# and maybe even with MSDN platform invoke? Yeah, then it will take you less time than if you don't have that. It also depends on the structure of the code and the complexity of the code. The OpenMI documents say count 3 months. And I once made an OpenMI interface for the groundwater flow simulation program FeeFlow that cost me more than 1 year, but here I had a special challenge that I did not have the source code. And for RTC tools, I had the first version ready after a week, but I had some experience already. In the Elbe flood, yeah, that was 1 month, and I also could benefit from previous coding projects. So yeah, I had some experience. I think yeah, it's not something you do within 1 afternoon.
Okay, thanks. That's very important to know. You already mentioned the spatial context. You said it could be also 2-dimensional, 3-dimensional components or coordinates. So it's possible to add spatial models to OpenMI. Did I understood it correctly?
Yeah. Spatial models, OpenMI 1.4 requires somehow a representation of time. So OpenMI 2.0 does no longer request a dimension of time, and this has been changed in order to support also tools and converters, yeah, without any time information. But spatial coordinates and I think also grid systems can be represented in OpenMI 1.4 and 2.0, so that's possible, yes. And if you use 1.4 and you add a dummy time relation, it shouldn't be any problem. So answer is yes.
Okay, thank you, Bernhard. I see no more questions. So it's time to wrap up this webinar. We would like to summarize with 3 take-home messages. We hope we were able to show you how to couple models and how to simulate interacting processes, that OpenMI offers the possibility to couple models in different ways, and how these decisions by the modeler influence the results, the performance of the model. And finally, that results in computation depend on the coupling properties. If you're interested in further information on OpenMI, you can check the website of the OpenMI Association. You can find there general information about OpenMI and the OpenMI Association. You can download the documentation and the source code of OpenMI 1.4 and 2.0. And you can find publications related to OpenMI. OpenMI is also available on SourceForge. You can find their source code, but also support in the discussion pages. And we have a Deltaris OpenMI public wiki page where we provide documentation, tutorials, some support, and we will place there the slides of this presentation. And also we made some additional lecture notes which provide additional insights we will place in the OpenMI public wiki. We would like to thank everyone for the interest in OpenMI and for attending this webinar. It was a pleasure to give this webinar today. We hope you enjoyed it as much as we did. Thanks especially for Bernhard to explain everything. Yeah, everyone, thank you very much and goodbye.